We're going to get into the really more meaty stuff later, but I'm going to breeze through this maybe a little faster. I'm going to try to scare you guys with protons, neutrons, electrons. Basically, at the end of the day, what is electricity, right? So electricity is a flow of electrons. We know that. And the flow is, I don't really care about electrons. It's current, right? And ultimately, how current works is maybe more for physics. But in terms of working on your boat, the thing you care about is current. And current is really flow, right? That's what it is. It's how something goes from one place to another. And water is an extremely good analogy with electricity. And we're going to be using that later through this presentation, right? So there you've got electrons here. We're showing electrons going through a wire. It's current. It's like water flowing down a pipe, right? And here's the really hard thing to grasp, and I get this all the time, is that the rate at which something is going, like kilometers per second, meters per second, right? That's a rate, right? Unit quantity over time. That's actually an amp, an ampere. So what that means is that it's already, there's no such thing as an amp per hour, because it's actually in this unit. Flow is an amp, right? So it'd be like speed is similar to an amp. Speed is distance over time. What speed are you going? 60 kilometers an hour, right? That's speed. Amps is the same thing, right? So amps is not over time. Amp has time built into it, okay? So speed and amp is very similar. We're not going to, it doesn't really matter. So different types of conductors, right? You got gold, you got silver, you got copper. That's starting to be pretty important, right? And the reason why we use copper on boats is because it's affordable. We don't use aluminum. And also over time, what people have been doing is they've been tinning the outside of copper, right? So there's still copper in the wire, but the outside is tinned. And the reason you do that is, I remember growing up and looking at all those beautiful Fairmont hotels, right? They have beautiful green roofs. Well, they weren't green when they put them on, right? They started off like copper, and then copper oxide happened, and now they're green roofs, right? And so when you see corrosion on top of copper, we're going to talk about that. That's a problem. That's a really, really big problem, and we'll get into that, okay? So we talked about conductors, and now we're talking about insulators. Insulators are the opposite of conductors. You got glass, you got ceramics, and on boats we use, obviously, most of everything is plastic, right? Because we don't want something that's brittle, and so we use plastic. Now, notice, this is a good little image. You can see actually different coins, different level of corrosion. But what happens with this copper oxide is it actually will start creating resistance, right? So now the conductivity of the wire that you had, once it's corroded, is going to be potentially fractions of what it used to be. Give you an example. I had a client, we were called in a little late in the game because he had paid someone to rewire his boat. The boat had flooded, bought it. He was told the boat had flooded just for a short period of time. Of course, what's a short period of time? Right? 3 days, a week, a month. It's short. It's all relative. Bought the boat, brought it to Vancouver, had someone rewire the boat. This fellow rewires the boat, and then this fellow's looking at things and he's going, oh, it's fine, it's fine, it's fine, it's fine, it's fine. The fridge, if the light in the fridge was on, the fridge had electricity. But the moment that the compressor would turn on, the light in the fridge would go off and the compressor wouldn't work. What had happened is the person that had rewired the boat made assumptions. Remember this theme about assumptions and how bad that is? Never assume anything, right? You shouldn't assume people's feelings. You shouldn't assume how you're doing, how your boat is doing. You need to find out. You got to be inquisitive, right? You got to look. The corrosion was so bad on that connection that you would measure it under no load, and this is where it gets tricky, and we'll talk about that later. You measure under no load, meaning there's no current going through it, and you'd have 12 volts at the fridge. You'd see 12 volts at the fridge. You'd measure right at the fridge, you'd break the insulation on the positive and negative, you'd see 12 volts. Perfect. Oh, the fridge is getting 12 volts. So it's connected to the battery, obviously, otherwise we wouldn't see 12 on the fridge. The light would be working, go down to about 11.5. You're like, oh, it's getting voltage drop. As soon as the compressor would go on, the voltage would drop to 2. Because resistance is influenced by the amount of current going through. So the connection was so bad that as soon as a little bit amount of current was trying to go through, it couldn't, and the voltage would drop. It's a little bit like having I'm not a medicine guy, but having corroded arteries, right? You sit on the couch, you're not doing anything, you're in bed, you're not moving, you're totally fine. You start shoveling snow outside, right? Now you're working hard, now you have a heart attack, right? So same thing, right? So what's complicated about that is that loading, i.e. how many amps are going in and out of a circuit, is going to affect the voltage drop of that circuit. So you can have something that's completely fine under no load, and then you apply a load, and it goes down to 2 volts. And because that connection was underwater and hadn't been changed, under load, it would cause a 10 volt drop. 10 volts. So that's why with copper on boats, they tin it, right? Another thing too, and we'll talk about, before I even go, so we're talking about insulators here, but I want to make a very, very important point. Again, another theme is no shortcuts, right? No shortcuts. Don't think you know better than everyone else and everyone's crazy and you're the smartest, because you're going to get yourself in trouble. I had a client, the boat came like this. He had welding wire on the boat, and a lot of builders put welding wire, not understanding the compromises they were taking by putting welding wire. They just didn't get it. They thought a wire was a wire. Looks the same, it's a quarter the price. I'm not stupid, I know better. Why would I pay 4 times when I can pay a quarter? Runs copper welding wire on the boat, great. Now luckily that builder was somewhat anal and actually took the time to actually run every wire individually against the bulkhead on its own. So they were stacked, one on top of another, but not touching. Not in bundles, which is a good thing, but that takes time. So luckily whoever did it, not the purchaser, but the technician, was pretty anal. So the wires are not in a bundle, and you'll see that's the only reason the boat is still here, and I got to see it. On top of this wire, that's welding wire, there were fuel filters. Raycar fuel filters, that's not unusual, right? Diesel engine room, Raycar fuel filters. When I did an electrical audit on that boat, I got in the engine room, and under the Raycar fuel filters, the welding wires, both the positive and negative going to the starter, leaving an 8D battery unfused because starters are not fused, were completely bare. Gone. There is no more insulation. It had melted away, not through heat, through fuel. The diesel fuel leaking out of the bottom of the Raycar fuel filters had actually melted the jacket, the insulation jacket off the wire. And now the only thing that saved that boat is the fact that the wires were actually running against the bulkhead and properly mounted so they wouldn't sag or touch another. Because if they didn't and they were in a bundle, the boat would have just gone. I mean, it would have been one of those morning shots. You go on CTV and you've got a boat somewhere in a marina on fire. And people are like, well, we don't know what happened, but something did. And then they're waiting to find out. So if you have welding wire on your boat, and a lot of us do, by the way, a lot of us do, like way too many of us, make sure that, and it's prohibitive to change all the wiring, but now you have to start taking precautions, right? Again, if you take a shortcut and you leave a trail, and you're like, I'm not going to follow the road. You know, I'm going to go on my own. Well, start preparing yourself. Bring a flashlight, some food, bring overnight gear. Tell people where you're going to go. You don't go in the bush without actually having a plan. So if you've got welding wire, make sure that that wire under no circumstances will ever be exposed to oil or fuel, ever, right? So it can't run loose at the bottom of an engine, right? Because you're going to have sometime maybe an oil leak or a fuel leak. If you have that wire, it's untinned copper, right? It's bare copper. So you should definitely have heat shrink, right? Because, I mean, you really want to protect that connection more than a tin connection. So on a lot of boats, we see welding wire. We don't tell the owner, you got to change it all. What we say to the owner is say, okay, now that we know that we have some sort of weakness, right? Let's offset that by making sure that we don't take other shortcuts. Let's make sure that we use heat shrink, that we use close-ended lugs, right? That the wires are never going to be exposed to any sort of fuel or oil, right? If they're in a bundle, let's make sure, let's fuse every wire, because what happens if for some reason there's a huge fuel leak on the engine, it does contaminate the wires and they do melt. Let's make sure that there's fuses. So it's all about knowing the risks and then offsetting them. In this picture here, what you see is you actually see they're fairly thinly strand wires, so that means they're really good for vibration, right? So you can see, I mean, there's, I don't know how many wires there are here, I mean, I don't know, 20,000, 50,000. When you look at, there are versions of older welding wire where the strands are pretty big, right? They're not fine strand like this. So the wires are stiffer, right? And so that's going to be a problem with vibration, right? Because when the boat vibrates, and if the wire can vibrate for a period of time, you might have, the connections are going to start. I've seen alternator lugs with welding wire, because an alternator vibrates a lot, where the lug actually sheared off. The lug sheared right off. I've seen alternators where the post on the alternator shears off. Now imagine if that happens on a positive. Remember, the whole engine is negative, right? So the whole engine, everything on the engine is negative, and now you have a loose positive wire that fell off the alternator. And a lot of people, what they do is they have those positive caps on top, but they don't use them. I.e., whatever reason, they needed to go see voltage. They took the cap down, put it down, and then when we're done reading the voltage, they didn't take the time to put it back. So now that lug, which is positive, has a cap on it, but the cap has been brought down, and now the wire is loose in the air without any protection, and the whole engine block is negative. So having tinned wire, fairly very fine strand wiring, what that's going to enable you is going to have the wire's not going to be as stiff, and it's going to be more corrosion prone. So I would certainly advise anyone that does work on their boat and is going forward, right? You can't fix everything behind you, but going forward, I think it's strongly advisable to buy marine grade wiring that is thin strand, right? And very, very tons of, for all the reasons that I mentioned, okay? And if you put it in your boat, remember a boat is not like a truck. It doesn't have a shelf life of 10 years or 5 years, right? Boats are 20, 30, 40, 50 years, right? There's tons of boats from the 70s, 80s, 90s. So if you do something on a boat, it's not like a car. It's not a 1985 boat or a 1975 boat is not an antique. It's just a boat, right? That's usual. There's boats out there that are from the 70s and the 60s, and they're not antiques. They don't have special plates. They're not collector's items. They're just a boat. So if you work on your boat, make sure that you do something so that it's going to last forever, okay? And that's how you do that with a proper jacket on a wire. So here we've got a little diagram. As you can imagine, what this is basically, we're measuring conductivity. So you've got on a multimeter, and I really like, digital multimeters are relatively inexpensive these days. And we'll talk about tools a little bit later on. But there's no reason why, and I would recommend anybody going offshore should have a clamp-on meter, by the way. Clamp-on meters are great because you can actually put them on any wire and clamp them on. You don't have to touch anything, and you can actually measure the current going through that wire. So it's really good to assess, like, oh my God, look at my fridge, it's drawing 5 amps, so my windlass is 70, my starter is 200, my fridge is 4, or my stereo amp is 7. And you can start measuring current everywhere in your boat, so you know what to fuse. You know if it's working or not, if it's drawing too much current, not enough current. And that's one of the modes of these multimeters. The other one too is, and you can see here, is you've got ohms. And this is an analog screenshot, but on here you've got the same thing. And I can set it to ohms, right? And ohms is where you measure the resistance, right? How conductive is something, right? Between A and B. And so here you'd have a positive and negative lead, right? Like on here, going on either side of a coin, and you'd measure what the resistance is. And a really good resistance is a low resistance, meaning 0 is perfect. It's a dead short. The higher the number, the worse it is.
Where do you measure the resistance at the coin?
Yeah, like for example, if you've got, this is a conductor effectively, it's a wire. So if you measure it here to here, then the resistance between those 2 points is going to tell you how conductive this material is. Okay? So back to what we were talking originally is this concept that currents need a circuit, right? There's a positive and a negative, right? And the negative is generally on the negative side of the load. So the positive goes to the positive side of the load, right? It could be anything, a light, it could be a heater, a fridge, and the return path is the negative. The load is effectively a resistance, right? That's what it is. And without a resistance, you have a dead short. So if you connect the positive to the negative on a battery, the wire is going to simply melt, right? And you're going to have a lot of smoke, and it's going to be really scary. The only reason you can connect a positive back to a negative is if you have a resistance of some sort. A resistance can be anything. It could be a light bulb, it could be a heater, it could be a fridge, it can be your GPS. All those things have a resistance. So it doesn't let all the current go through, right? It lets only part of it so that the wire doesn't get overloaded, right, as a dead short. So here's what we have. This would be a good example, right? You've got a positive going to a bulb, right? It goes through and then comes back out, goes back on the negative, right? Does that make sense? And over here, what you've got, an open circuit, is they actually ended up putting a switch, right? Over here. What this is simply a switch, right? So it's a breaker, right? So it's always connected to the battery because you don't want to start having loads come on and off by taking loads off the battery, right? Literally, you want to have the convenience of having breakers, switches, right? And so what you have here is you have effectively an open circuit, right? Because with this switch being open, current can't go through. Any questions on that? Feel free to ask questions. There's no such thing as...
So what stops the current coming out of the battery and then open? Just because
right here. That's what stops it.
it doesn't just flow out somewhere?
Well, it's getting up to here and then nowhere else. It goes from here to there and it stops because there's no circuit. It's waiting. It's potential, right? It's got this, let's say this is a battery. Let's call it 12 volts, but it could be anything. It could be 3 volts, 9 volts. This and this is the same thing, right? Here and here is the same thing. But right now, it wants to get back to here. It wants to complete a circuit, right? It wants to go back to ground, to the negative, right? That's what it is. It's trying to equalize itself, right? It's trying to have everything at the same level. So the 12 is trying to get back here. But because this is open, the switch is open or off, then the circuit is open right now and not working. Yes?
Back to the ammeter. How does it work without actually touching the conductor?
You have, oh, this one here? Oh yeah, that's called flux. You know that's why they don't like people don't like living under power lines?
Right.
That's called magnetic flux. So magnetic flux is where, now this is where my physics in university comes handy. If you take a conductor and let's say the wire is going this way for DC current, you'll actually have magnetic flux is going to be this size. So the orientation of the magnetic field is going to be wherever the direction of the current is. For alternating, it's actually going back and forth, right? So you have actually an AC clamp meter or a DC clamp meter, and this does both. And then you can actually see the rate of the flow. Is it a charge, like current, or is it a draw going the other way? So the orientation that you put this, or like this, you're going to get actually a different reading, right? So positive or negative.
How do you properly use one?
Well, I mean, think about it. How often do you not know if it's a load or a charge, right? If you're measuring a charger, the fact that it gives you a -20 reading, does it really matter? You know that your charger's not drawing 20 amps. You know that it's outputting 20, right? So if you put it like this on on the line or you put it like that, it's still going to give you either minus 20 or positive 20. It's a charger. If you wanted to know for sure, you'd have to make sure, like you're like, am I charging or discharging as an overall sum on my batteries? That's where the polarity would matter most.
Well, say like my panel needs, I'm putting up 60 amps on my batteries or something. So you put your clamp around the lead that's off the alternator.
Yeah, you could, and that would measure just the alternator output. And you'll see the,
Right way and a wrong way to do it.
well, you're going to see the wrong way would give you a negative and the positive way or the right way would give you a positive reading.
Okay.
It's just a polarity.
Never used one.
They're great. Now, don't go to Home Depot like I did, because when I bought my boat in 2006, I felt justified to buy every tool known to man, because finally I had a boat, and I was like, well, now I have to buy tools. So I went to Home Depot and went to town, and I bought a clamp-on meter, and that clamp-on meter is still at work as a reminder to do your research. Because it's an AC-only clamp-on meter, and an AC-only clamp-on meter is really not useful. It's great for home work, but not for boat work. And I use it, and I introduce it to everyone in my shop about doing their research. And this is my proof, right? It's my burnt. Like, I remember that. And it was expensive, but it's useless. Because realistically, how many AC circuits do I need to measure on a boat? It's DC that I really care about. So when you buy one, make sure that it has AC and DC.
So what is that one?
This one is from Blue Seas. And I don't know, they're maybe $100, $150. You can buy them on Amazon. You can buy them everywhere. They range. I mean, the Fluke ones get more expensive, but you can buy something like that from Blue Seas. It does up to 400 amps, which is plenty.
What's the minimum, like, can you, if you spend $50 on one?
I'd say probably Amazon is probably 75, probably. But Amazon is like, you know, I mean,
As long as it's AC and DC.
yeah, and also the range of the DC, right? You want to have at least up to 200 amps,
Okay.
right? You don't want measuring only 20 amps, right? Because what if you're windlass or your starter circuit, right? Yeah. So, and they're digital multimeters as well. Yes, go ahead.
So you're not gonna, like, a lot of us, maybe me, but we figure we're gonna electrocute ourselves if we take that and put it on something.
No, you're not going to execute yourself at all.
Okay.
No.
It's not gonna be a flash or you burn your hand or.
Now, really interesting point. No, this is really good though. This is really good point. The worst thing you can do with DC is cause a fire, right? If you take a multimeter and you end up shorting the positive and negative of these, you can cause a fire, you can cause smoke, maybe burn yourself with DC. That's pretty much it, right? At 12 volt systems. And that's fine, and if you're comfortable with that, you know, because being burnt is not that big of a deal. It isn't. Now, the one thing that is a really big deal, and a huge deal, is an AC system. So I strongly advise that no one play with in the back of an AC panel that is 120 volts, alternating current, where your life is at stake. Because it actually can screw up the rhythm of your heart. I don't know the term, I've been told, I forgot. But that's what is dangerous about AC. It's not the fact that it's 120 volts, it's the fact that it's alternating current. And it puts your heart out of sync, and that's how people die electrocuted. Not because it was painful, because pain, whatever, you'll get over it, right? The heart attack is it's not a heart attack, but your heart will stop. I don't know, there's a word, anybody maybe is a nurse or a doctor.
Fibrillation. It fibrillates. It's near death.
Yeah. So it's pretty serious. So with AC, I don't recommend anyone open the back of an AC panel and start playing around with AC unless they are absolutely confident that they will never make a mistake. Because if they do make a mistake and they cause a dead short or they touch something that they thought was not hot or energized and they could die. So that's really, I think, for me, when I tell owners, the differentiator is that with 12 volts, the consequences are there, right? Boat could catch on fire, you can do certain things. But with 120, you could actually die, and you'd be die on your boat. The boat would be completely fine, but you'd be on your own, and you're done. So don't play with 120 AC. And on a boat, it's actually more complicated at home. There's multiple sources of AC on a boat. It's not always just dock power, right? There's inverters that can be on what are called standby modes. I've had owners that are smart, right? Know everything, right? So And then they share their stories, and they're extremely humbling. So they have an inverter, and they're going to be changing an AC outlet on their boat, right? They've done house wiring. They've wired a house. They've done everything. I mean, they know this is easy. I got this, right? So they're playing. They have an inverter on board, and they're going to use something like this to confirm if the inverter is on, right? So they're putting this in the AC outlet, and they're telling their sweetheart, they're like, look, babes, I got this. You see, I put it in the AC outlet, right? There's no lights. There's no AC there. I've just done a test, because if there was AC, I would see a light. You know, one of these lights would come on, and I'd have AC. But what they don't realize is that an inverter has a mode called standby and a mode called load sensing. Load sensing is where the inverter is waiting for a load that you set, by the way, of maybe 50 watts. This is not 50 watts. So this goes in the AC outlet. The AC outlet doesn't sense a big load, doesn't turn the inverter on. Now you start playing with the AC outlet. You think the circuit is not energized, and you're right, it wasn't energized until that point. You now take the AC outlet out of the wall. You put your fingers, you start grabbing it. It's perfect to be grabbed. You put your fingers on both sides between the hot and the neutral. Now that's more than 50 watts. Your inverter says, oh my God, look, my owner really wants to start running AC. He's just applied a load bigger than 50 watts. Let's automatically turn the inverter on, and let's give him seamless AC power. And it turns the inverter on.
Why would you mess with anything without disconnecting all this stuff?
Because people assume, that's right, people assume that if they do this, it's enough of a test, right? Because you would think this would be great, or they'll use this. That's what you do at home. That's why things are not transferable. They'll use one of these, right? Little wand, right? You get it beside the outlet. If it was energized, you'd see the light, it would flicker, it would tell you the outlet is energized, right? Don't play with it. Both these will fail with an inverter if it's got load sensing enabled. Right? Because the load sensing is not measuring current. This is certainly not taking a load. And this is too much of a load. This light is not 50 watt load. And so the inverter's on standby, waiting for someone to cause a short of a watt more than 50 watts. They take the outlet out. They create with their own hands a short. And then the inverter goes, okay, now I need to start working. And then the owner got electrocuted.
So there's no voltage at a plug for an inverter until it's activated?
Well, not if you have load sensing on.
Wand,
Yeah, there's none.
got some pretty low.
There's no voltage. Because the inverter's on standby. It's load sensing. It's doing that to prevent the inverter from creating power when you don't need it.
So you just have to turn your inverter off.
And how do you turn your inverter off? That's a really good question, by the way. That's a trick question.
If it's on charge only, like ours has a charge only setting.
Yeah.
It is not on if it's on charge only, correct?
Right? Correct, yes. But what else do you do? Now think about what are the ramifications of not doing this properly.
Well, if you turned off the master, we've got a master.
DC disconnect. Yeah. Most inverters don't have one. Why? Because no self-respecting man is going to read a manual. It's crazy. It's humbling. I mean, why? I'm not stupid. I don't need to read a manual. I was born with knowledge, baby. I got this. I learned this through osmosis. It's just that simple. I've done this all my life. I got this. Manual, it's for engineers. They're stupid. This is ridiculous. So most inverters are not installed to code because the manual, when you buy an inverter, we'll talk about that later, the inverter doesn't actually come with all the pieces you need to install an inverter. It's like you just buy the inverter. There's a lot of other parts that go to installing an inverter that don't come with the inverter, like a master DC disconnect switch, like a Class C fuse block, like appropriate size chassis ground, like the right size wire gauge, right? All those things don't come with the inverter, and so people don't install them because they didn't come in the box. This is not IKEA, right? It's not, you don't buy a boat or an inverter system when you buy an inverter. You're buying a part of a system. You have to read the manual, which is 100 pages, and you have to look at what is the situation for your boat, and then find out all the other pieces, and you got to go shopping for those pieces, and then you have to install them. The problem is that most people are satisfied with something working. So if possible, people would drive a car without seat belts. If it was an option, most cars would not have seat belts. They wouldn't. People would say, why do I need a seat belt? My car is fine without one. They would have probably no tail lights. They'd probably have no emergency brakes, because all those things are only in the event that you might need them. And a master DC disconnect for an inverter is something that you would use if you were ever going to work on your AC system, right? One of the questions I always ask people, I say, if you were going to work on your AC system and you don't have an inverter, what do you do to feel pretty safe that you don't have AC system on your boat? An energized AC system. What would people in the classroom, give me some examples of what you would do?
Unplug the shore power.
Yeah, why switch off the brake, disconnect the shore power over the breaker? Why would you say not the breaker, for example? Why did you say disconnect?
You still have power, because that's one absolute thing that you. Right?
Exactly. That's the reason. Absolute. And why does absolute matter? Because it's your life. I mean, what in life is more important than your own life, right? That's it. All this is, remember, and I always remind people, I'm like, none of us are boating to make a living. This is pleasure boating. This is not, oh, I'm going out there fishing for my family and I got 12 kids and I got to make it work and I got to just do it. This is actually a recreational activity that we do on the side, right? And so I always tell people, with AC, you need to go black and white that nothing is energized. And I agree with you. I would never trust an AC breaker on a boat, because you're trusting a breaker. That breaker doesn't say, by the way, I have an unconditional promise that if it fails, it's going to fail the right way. And if it doesn't, oh, I'm going to make you come back to life. Right? Like, what are you going to do? Like, you're going to sue the breaker? You're dead. There's nothing, why trust that, right? So you disconnect the shore power. You don't disconnect it at the dock. Why? Because someone might think that it's got disconnected accidentally, right? You take the shore power, you completely remove it. If you were an electrician, you would actually tag it, meaning you shouldn't, like, they'll do that in industry, right? They'll tag it, you can't energize. Turn off the breaker, you go multiple steps to make sure that that boat will not be energized while you're working on the AC system. And for an inverter, it would be the same thing. With an inverter, you're not going to go on a panel and press an on-off button, a little tiny little button that sends a data signal on a telephone wire back to an inverter to trust your life. You're going to go, okay, I've disabled the inverter, but you know what? I don't trust that. You're going to do, the second thing is you're going to do what they have on their boat, which is what the code says, and you're going to go from the switch from on to off. And now you disconnect DC power from the inverter. Without DC, the inverter can never work, right? And that's what you should do when you're working on your inverter or shore power and AC, is you got to go really safe. So as a long story, but it's really important, especially back to the safety thing, is be really cautious with inverters on your boat, because they have this mode called load sensing. Okay? And these things would not, you'd think you're genius with both of these. Like, you'd be for sure you got this. Right? Both would give you negative answers. But they were both wrong. Because there was no AC there until you became a load.
So if you disconnect, if you turn the DC disconnect off, that's just to the inverter, right? You still have your 12-volt
Oh, absolutely.
line.
There should be completely separate. That should be an inverter disconnect switch.
Yeah.
Yeah, and they're completely separate.
Your lights to.
Absolutely, yeah. And some people, again, take a shortcut, don't understand what they're doing, and wire an inverter to the house side of a switch, because they're like, oh, I already have a switch. They told me to use a switch, but they probably don't know what they're talking about. Again, I'm an expert. I will do it a shortcut way, and I'm going to wire my inverter to my battery switch that's already there. And there's tons of pitfalls with that. You always have to follow instructions to the letter, unless you're an expert. And an expert doesn't mean you wired a boat. It means you've wired hundreds of boats, and it's your profession. Nobody's going to be an expert at wiring a boat because they wired their own boat. I mean, I'm sorry to say, you're not going to. Some of my guys have 20 years of experience. You know, that's crazy. That's 40,000 hours. That's an expert. You don't become an expert without, the expert rule is 10,000 hours, right? That's kind of the mode. You're not going to be an expert wiring your boat because you've wired one. That doesn't make you an expert. And as smart as you are, and there's nothing wrong with that, practice makes perfect, right? That's really the difference. I've hired engineers that are super smart that are completely useless wiring a boat. They're great, top A's, best grades, but practice is important, right? That's why people that do trades have to do practice. Yeah.
And sort of subsequent to what Blair said is that if you have the boat with all the battery switches and turn everything off so that nothing works at all, is there still 12 volts sitting there waiting to be used? But if you turn off everything, like the Junos have the negative ground.
Yeah, we're not going to go there.
Okay.
We're not going to go to the negative switching.
Okay.
But yeah, generally you would assume that if you turn the switches off, you don't have power. But again, that's an assumption that over time has been, that's probably going to be more wrong than right.
So you take everything off.
Well, you wouldn't need to because you need to work, you need light. If you're going to work on an AC system, you're probably going to need light. So you don't have to do that. You need to make sure that your inverter has a switch. And you need to know that that switch is an inverter switch, right? Again, you can't assume. So you got to confirm. And then when you do that, you can just disconnect that and then you're fine. And then you can still have the 12 volt energize and work on your AC 120, right? They're separate. Okay. So that was a long-winded side, but I think it's important to always remember if you're going to work on 120, be extremely cautious. 12 volts, there are implications, but none as serious as losing your life, easily. Okay? So here we've got, what's an electrical short? I've been using that term, like electrical short. A short is basically 2 points of a battery, the positive and negative, without any appliance, right? So it could be, for example, a positive and negative wire leaving a battery going, it's a duplex, meaning two wires are now part of one cable, right? So they're coming, this happens all the time. You can buy duplex wiring, triplex wiring. So you'll have two wires that go into one cable and they're running down. Most wiring on a boat is duplex, right? A positive and negative together running some distance to an appliance, right? Because it's convenient instead of running two separate wires. But it doesn't matter. It could be two separate wires running one beside another. They're not going on opposite sides of the boat. They're going to a light. They're going to a water pump. They're going anywhere, right? They're going to all these different points on your boat. If you ever take and put a screw between a positive and a negative wire, right? Because you're drilling, you're putting a light switch on your bulkhead. You don't realize there's a wire behind it. And you put a screw, you could cause a dead short between the red and the black. And then I'll show a video a little bit later on after we come back from lunch. I'll show a video about that. Where those two wires now, there's endless current flowing through here, right? Because there's no more resistance, right? Because the wires have practically no resistance. I mean, that's what a wire is. It's very conductive, right? So now you have a perfect circuit. And what's going to happen is the wire can melt, the biggest cause of boat fires. And if you don't have a fuse, the boat, literally, that wire is going to become literally lava hot. Like it will get hundreds of degrees. And the issue is the wire might melt and become in itself a fuse, and I've seen that, where the current going through the wire is so much that the wire can't handle it, and the wire actually breaks and melts off. But when that happens, until the wire melts, everything around that wire, which remember on boats we have bundles, right? Wires are not going one at a time. Wires go together, they go up, they start aggregating, right? Then that wire, when it's melting, melts all the other wires around them. And then I've seen wires go up pipes, you know, from a, let's say from a fly bridge down to the lower helm or upper helm, and they're going up these conduits, where the whole bundle melted together. Because one wire melted, and that caused the other wires to lose their insulation, which causes them also to short, and then it was a full domino effect.
So the best scenario in that case is that the wire actually melts through.
Yeah.
And breaks the circuit.
If your approach was not to fuse. And I would say that it's utterly criminal. If you had an electrician come to your house or your place of business or your commercial place, whatever it is, your condo, and he would say, listen, you wanted some new appliances? I think this whole breaker panel thing is just so yesterday. We're just gonna go hot, right? We're gonna bypass, it'd be dead simple, by the way, and that's how grow-ops work, right? They live on the edge, right? So we're just gonna go right hot. We're not gonna put a breaker in because, you know, what's the chance that you're gonna use a breaker? I mean, it's not likely gonna happen. You're gonna be safe, right? You're not gonna overload the breaker or the line. No, I won't do that. Okay, perfect. Save you a breaker, right? Takes less time. We're all good. What I just said here sounds absolutely insane. Well, I hope it does. Happens to every single boat that we've all owned. And I don't mean once. All of us, every boat you are ever going to buy or own, unless you're this exceptional boat and it was built by a factory. Factories are different because they do what I'm going to say. Every boat that leaves a factory is going to have someone that's going to work on that boat, and that someone does not understand what I just said, and they're going to take shortcuts. And not fusing a wire, on some boats, it could be every single wire. You could have 50 circuits that are unfused, 20 circuits, 10 circuits. Every other new circuit is unfused. They put fuses in the wrong places. They think the fuse is only for the appliance. They fuse no wires. The wires are completely unfused, and they fuse only the appliance. It is the Wild West for fusing on a boat and breakers. The Wild West. Or people think they have a large fuse at the beginning of the circuit and it protects their whole boat. I'll show a few videos when we get back after lunch. I've got 4 videos that we did that are amazing demonstrating this. So the point is, you absolutely black on white have to fuse every single circuit on your boat. And the location of that fuse does matter, and it should be at the beginning of the circuit. And if you're going to have 2 fuses, you're going to have one for the wire and then one for the appliance. Right? That's fine. You could have a fast blow 7 amp fuse for a VHF, and then you can have a gauge 10 fuse for the wire. Right? A fuse for the line and a fuse for the appliance. When you're going to buy your boat, and most of us buy not brand new boats, I can tell you that never assume that your boat is properly wired. And 99%, well, it's more than that, every single one of us that are going to buy a boat are going to find unfused circuits on their boat. It's guaranteed. Guaranteed, because it works without the fuse. And that's the issue. Right? Like you can drive a car without a seatbelt.
So in a factory boat, from a reputable builder,
All builders are going to fuse.
so it will just be done that way.
Perfect. Yeah, absolutely. They're engineers. They're like me. They're crazy. That's what we do. It's all about, you don't live your life thinking that things don't happen because the consequences are too grave. And a builder like an Island Packet, it doesn't matter. Catalina could be a Bayliner, it could be a Hunter. I mean, Catalina is not a high-end boat. It's a Renault, it's a Ford, it's a low-quality boat builder. I mean, they're about volume. And that's what I have. They fused every wire at the factory. But what happens is over time, that boat starts being modified, added on, do-it-yourself projects, so-called professionals. And then those people are people that don't understand the implications about fusing, right? And they put the fuses in the wrong places. So you would never worry about a boat from the factory, ever, almost. It's impossible. Too much liability. You would worry about the projects that happen afterwards. Do you have to worry? Any other questions on that? Yes?
Will you later describe where the fuses should
Yeah, I'll do. I've got 4 videos that are amazing. Amazing videos. I'll show that. All right, so what is voltage? Voltage is really like pressure. Voltage is like, and pressure could be a good way to look at it, would be height of a water column, right? You know, like when you dive in a pool and if you're 2 feet or 4 feet or 6 feet or 10 feet, you have more pressure, right? So 12 volts is really the amount of pressure, and you can see this is smaller, 1.5, and you know, some boats have 24 volt banks, and some older boats have 32 volt DC banks, and 120 volts AC, 220, right? There's all these different potentials, right? And that's what it's called. The slides try to compare, and I agree, I think it's a really good way to think about the higher the height of the water column, the more pressure you're going to have. Right? Think about the Hoover Dam, right? Like they talk about people that have to dive those dams that go on the inside, right? The pressure that is at the bottom of a water column that's 500 feet is insane, right? You can't just go there willy-nilly. You have to be, it's a completely different experience. Same thing with voltage. So that's why 12 volts, and you can burn yourself. 12 volts is really hard to burn yourself, but certainly as the voltages go up, there's more and more chances of burning yourself. So voltage is like water pressure. The greater the voltage, the greater the potential energy. So now if we're thinking about resistance, what is resistance? Well, resistance is limiting effectively the flow, right? Because that's what it is. I mean, it looks like a weight that basically a choke point. It'd be like putting your foot down on a water hose, right? Or kinking a water hose, right? So you're limiting that flow so that it's reasonable amount of flow, right? And that's what a resistance is. And resistance is also another word for load or an appliance. A water pump is something that is inherently resistive. Every appliance that you have on your boat, your LED lights, your chart plotter, your radar, everything, your stereo, your TV, all those things, all these loads, all these appliances have a resistance to them. That resistance makes sure that the positive and the negative wire are not in a short circuit. There's something in between that limits the current going through that wire. Right? So that's why you can never have a positive and negative wire connecting directly. If you do, that's called a short circuit. Right? That would mean unlimited amount of power going through that cable or wire. Okay? So stepping on a hose will create resistance. Right? And ultimately, like a water hose, it slows down the flow rate. I mean, we've all done this probably. A water hose, you want to take something off, you're walking with it, you kink it, and the water coming out of that hose is going to be of less volume or flow than before you kinked it, right? So if you, and this is good, people, and you remember that, you see all this ties back to the images we're talking about. Remember the chassis ground with the inverter. The builder went to the time of putting a nice big cable, right? And then someone was like, oh, it's put there. They must have put it there for a reason. They put a screw down on the floor. They probably want me to tie it back to there, right? This big cable. I'm not going to bring that to the inverter. How am I going to do that? Oh, I got this. I'll just put a small little jumper. Well, if the cable was 2 watt and you're putting a jumper cable that is number 10 gauge, and we'll see that gauge of wire goes, and this is like the opposite of the metric system, unintuitive. Right? Because at one point they thought the largest wire was going to be 0, and then they realized, oh crap, there's actually bigger wires than the 0. So they started at, like, say 26. 26 is the smallest, which is crazy, and they go down, right? And the smaller the wire, the bigger the wire, because I mean that's how you would do it if you were Imperial. It can't make sense. So they go down, and then they got to 0, and they're like, oh, the wires need to be bigger, and then they start going, okay, 0, 1 aught, 2 aught, 3 aught, 4 aught. Right? Because they had to go past what they thought was going to be the biggest, as opposed to start at the beginning, smallest wire being 0, or what they do in Australia, and they just talk about the diameter of the wire, which would be so much simpler, but we can't do that way. So unfortunately, in North America, we've got to think about wire gauge from, let's say, effectively on a boat should be about 22 to 4 aught. So on that inverter, they had 3 aught wiring for the chassis ground, or I think it was 1 aught. So pretty big wire, and then they installed a small little jumper that was 10 gauge. Well, the 10 gauge wire is effectively limiting the current because a 10 gauge wire can only take about 30 amps. That's what it is. I mean, I just know that off, there's charts, but I know that off the top of my head. So you can only take 30 amps. So the whole purpose of having that 1 aught cable is completely defeated because that wire can now only take a load of 30 amps. And once it's going to be more than 30 amps, what's going to happen is that wire is simply going to melt and it will open circuit. So effectively what they did is they put a resistor. They put a resistor that's for 30 amps, is what they did, right? Right? And that's kind of like what this looks like, really. Imagine that was the inverter here. They have a, right? So that stud can handle so much current. They put a little 10 gauge wire here, and then they went to large gauge. Well, that is effectively a resistance. All right. So here's another example, a light bulb, right? The incandescent light bulbs that we're all familiar with. That light bulb inside, that little filament is a resistance, right? And as electricity goes through that filament, it actually heats up, and the heat is actually what creates that light, the glow, right? All right. So question, if we increase voltage, will the electrical current increase or decrease? And anybody remember what the formula is? V, voltage, equals current times resistance. That's R, yeah. And I'm spelling it R. It's V equals IR, but people are always asking me, what the hell is I? Current. Okay, so voltage equals current times resistance, right? So if you increase voltage, what's going to happen to current? If V equals IR, if you increase V, then current is, oh, sorry, I went forward. The current will also increase, right? You increase voltage, so will the current. What about this question? Now, what if we increase resistance? What's going to happen to the current? Because remember now, voltage is on one side of the equation. The voltage is not changing. You're increasing the resistance. What's going to happen with the current? Is it going to increase as well or decrease? That's right, because you have to stay the same. The current will decrease. Okay? Proportionally, right? So if current goes up by 20%, resistance has to go down by 20%. And that's the key. And that, by the way, if your takeaway today is one of 5 things, the biggest takeaway you can remember is that if you increase resistance, let's say you have a bad connection on your windlass, it's corroded. Windlasses are in the worst place on earth. I mean, the Ford locker, I mean, it's hell. I mean, that's the version of hell. Like, that place is just awful. So you went in, you didn't put heat shrink terminals, you didn't put a tin lug, you use a welding wire. I mean, you know, you just said, because it worked the first day you put it in, right? I mean, but a windlass, it's the worst place on a boat. I mean, it's truly wet, humid, the worst. Now that connection over time, it worked the first day, remember, because the first day, it doesn't really matter. It's the first day. Now that connection is corroding over time. Now guess what's happening to the current as you have bad connection? Much higher resistance, right? Now, but this is where, yeah, so you would think the current would go down. But wait a second. That's if V equals IR. There's another formula which gets really interesting, which is power equals voltage times current, right? The windlass always wants 1500 watts or 1200 or 1000 watts. If the current is now having to increase because of the resistance, or because of the resistance, sorry, let me rephrase, if there's a voltage drop because of the resistance, right, and you're losing 20% of voltage drop or 30% of voltage drop, the current going through the windlass is going to have to meet an increase proportionally. So that windlass, when you bought it, only ran 100 amps. But now it's running 130 amps, right? And it's running 130 amps, and I was on a boat the day before yesterday, exact scenario, the breaker was always tripping every time they'd use the windlass. Because the connection at the windlass was so corroded that it was causing a voltage drop, and that because of resistance, and that voltage drop was making the current have to match it more to offset the drop. And that's how windlasses die, for example, is that there's more current going through that windlass than it was meant to be. And most people don't put a proper size breaker on a windlass because they can't find one or they don't have one. And then they just kind of, well, it kind of works. And so they don't think that they need a perfect 80 amps. They'll be like, oh, if it's a dead short, what's the big deal? But what happens with windlasses is they don't die from dead shorts. They die from running too much current because of bad connections. So every voltage drop is matched with a current increase because of power equals VI. Yeah?
So what's happening when you can go from 12 volt to 24?
by half.
by half.
Yeah.
So what's happening there?
Well, it's because you've got a much higher voltage, so you don't need as much current. Yeah, that's right. Yeah. And that's also the problem when you buy European boats, is they're 220. And so they wired the whole boat 16 gauge, right? For their 220 outlets. And now you want to convert those 220. Let's say you take all the appliances out. You're like, oh, screw it. Scrap everything, and I'm going to reuse the wire. Well, what they did is they're going to wire everything 16.3, not 14.3. So now you try to take your panel and you change your panel to 120. But now the whole boat's everywhere throughout the whole boat, everything is 16.3. So it can only handle half the current. And that's why it makes the conversion process painful. So current is I, right? Voltage and resistance. So V, you remember, I mean, this is all, but like, you remember you can move things around. So you've got voltage here. You can take that, you can move it here, right? So voltage is equal to current times resistance, right? So V equals IR, right? There's all these different permutations, right? Because it depends what you want to calculate. In this instance, they want to calculate current, so they take voltage divided by resistance. Right? There's 3 variables, so you can figure out what you want. The units of measure, current, like speed, is in amps, right? It's the voltage. We know that's potential. And resistance is ohms. Okay, those are the units of measure. So here's another example. We've got Ohm's law. So we've got a resistance of 2 ohms, and we're a 12-volt battery. And how we know it's a current, we don't know what the current is. The only way we do that is we calculate 12 divided by 2 equals 6. Does that make sense? They're not, by the way, nobody's ever going to tell you when you're going to buy an appliance, and this is why I tell you this is somewhat dry. Nobody tells you the resistance of anything when you buy anything, okay? This is called like the foundation of electrical. You'll never think resistance on your boat, period, other than knowing that more resistance is bad and you want good connections, right? That's all you're going to care about. You're not going to buy a water pump or an inverter and it's going to talk about resistance. It's going to talk about wattage. We'll talk about that later, right? Ultimately, everything is about wattage, not resistance. And so if you buy an appliance, and I don't know, it could be a radar or chart plotter, they're not going to say this has a resistance of X. They're going to say, oh, you need to fuse this for 5 amps, right? They're going to give you that number right away. Nobody's going out there, unless they're MacGyver, calculating this, right? You're going to buy a VHF, and they're going to say, I want a 15 amp breaker. You're going to buy a water pump, I want 12. Whatever it is, solar panels, I want this, right? The manufacturer is going to tell you what amperage you need, right? Based on what they figure the load is of that device, right? So they're going to give you a little bit of safety room. Like if the light draws 5 amps, they're not going to say to fuse at 5. They might say, I want you to fuse at 6.5, right? So I'm just using the word resistance here, but don't worry, you're not going to be calculating this when you do work on your boat, okay? Here's why you care about resistance, right? Ultimately, all appliances want a certain voltage and are expecting a certain current, right? What can happen is if you have more resistance, right, you're going to have more voltage drop and concurrently more current increase, right? And that's the problem, is as you bring down the voltage because of resistance, the current is going to have to offset it, okay? So you don't want you want to make sure that all your connection points are done properly as to minimize resistance, okay?